Your phone is one of the most sophisticated pieces of technology ever created. It has more computing power than the systems that put humans on the moon. It connects to satellites orbiting 20,000 kilometers above the Earth. It can translate 100 languages in real time. It knows where you are within 3 meters anywhere on the planet. And yet, it dies after 8 hours of heavy use. It slows down when 50,000 people are in the same stadium. A stranger sitting in the same cafe can steal your banking password, and writing a full university assignment on it is a genuinely painful. Why? How can something so powerful have such significant limitations? That is exactly what we are exploring in this lecture. The challenges and limitations of mobile computing. And I promise you, understanding these challenges is just as important as understanding the capabilities both for your exams and for understanding how the technology around you actually works. Before we go through each challenge individually, I want to give you the most important insight of this entire lecture, one that will help you answer any exam question on this topic with genuine understanding. Look at this slide. On the left side are the strengths of mobile computing. On the right side are the challenges. And notice something. Every single challenge is directly caused by a strength. Probability, which we praised in lecture 3, creates the battery problem. Because the device moves with you, it cannot be plugged into a wall continuously. It needs a battery, and batteries are finite. Wireless connectivity, which enables seamless internet anywhere, creates bandwidth limitation because the spectrum is shared and wireless signals degrade with distance and obstacles. Always being connected, which enables real-time applications and instant communication, creates a massive security attack surface. The more connected you are, the more ways an attacker can reach you. Small and lightweight design, which makes portability possible, forces comprises in CPU, RAM, storage, screen size. You cannot fit a desktop processor in a device that weighs 180 grams, traveling anywhere, everywhere, which is the whole point of mobile computing. Means you connect to dozens of different networks with unknown security, unpredictable coverage, variable signal quality, personalization, which makes mobile experiences so powerful, means the device holds enormous amounts of sensitive personal data that make it a high value target. So, when an examiner asks what are the challenges of mobile computing, don't just list them. Explain the trade off. Explain why the challenge exists. That understanding is what separates a 7-mark answer from a 10-mark answer. Challenge 1, limited battery life and power. The most fundamental constraint of mobile computing. The core problem is simple and unavoidable. Mobile devices run on finite batteries. A desktop computer draws power from a wall socket. It can run indefinitely. A mobile device carries its power supply with it, and that supply depletes with every single operation. Look at the bar chart on the left side. What drains your battery most? 5G and LTE radio transmission takes the biggest share, 28% of your battery consumption. Every time your phone communicates with the tower, sending data, receiving notification, making calls, the radio transmitter fires up. And 5G, while faster, uses significantly more power than 4G. Screen displays next, 22%. Your OLED displays beautiful, bright and power hungry. Maximum brightness in sunlight can drain a phone in 3 to 4 hours on its own. GPS and location services, 18%. Continuously communicating with satellites, calculating position, updating maps. This is surprisingly power intensive. Apps and CPU, 16%. Running apps, processing data, rendering graphics all consume CPU cycles, which consume power. Wi-Fi and Bluetooth, 10%. Even in low power mode, these radios are constantly scanning for networks and devices. Now look at the solution on the right because engineers have been working hard on this. Low power processor. ARM chips like Apple M series are designed for maximum performance per watt. They have efficiency cores that handle light background tasks using minimal power and performance. Cores that only activate for demanding tasks. Battery technology advances. We have moved from lithium ion to lithium polymer batteries, which are thinner and more flexible. Solid state batteries currently in development promise twice the energy density with improved safety and no degradation over time. Fast charging. Qualcomm Quick Charge and OnePlus Super Boost OOC 100 watt can charge a phone from 0 to 100% in approximately 15 to 20 minutes. This partially compensates for limited capacity by making recharging fast. Adaptive power management. Modern operating systems continuously monitor battery level and usage patterns. When battery drops below 20%, the OS automatically dims the screen, reduces CPU frequency, disables location services, and pauses background app refresh. Energy harvesting. Solar powered phones like QoS models kinetic energy charges that harvest energy from your walking movement. These are niche solutions today, but point toward a future of self-charging devices. Second challenge, limited bandwidth and network issues. The core problem, wireless spectrum is shared limited resource. Think of it like lanes on a highway. Highway has a fixed number of lanes. When 10 cars are on it, everyone moves freely. When 10,000 cars pile on, everyone slows to a crawl. That's exactly what happens to wireless bandwidth. Four specific network challenges. Spectrum congestion. This is the IPL problem. When 50,000 fans packed into Narendra Modi Stadium in Ahmedabad for the IPL final, every single one of them is trying to use 4G simultaneously. All of them are on the same tower. The tower has a fixed bandwidth capacity. It gets divided 50,000 ways. Your speed drops from 50 Mbps to under 1 Mbps. Instagram won't load. WhatsApp message fail to send. Video calls are impossible. This is not a theoretical problem. It happens at every major concert, sporting event, and public celebration. The New Year's Eve crowd in Mumbai, the Kumbh Mela, all notorious for network congestion. The solution is 5G Massive MIMO towards towers with 100 sharp antennas that can serve many users simultaneously by focusing signal precisely rather than broadcasting in all directions. Signal interface. Signal interference. Your phone operates on the specific radio frequencies. Multiple things interfere with those frequencies. Walls absorb signal, buildings create dead spots, rain and humidity attenuate signals at higher frequencies. And other devices compete for the same spectrum. Your neighbor's Wi-Fi, your own microwave oven, baby monitors all operate on the 2.4 GHz band and interfere with each other. 5G's beamforming technology focuses the signal like a laser beam directly at your device, dramatically reducing interference, dead zones, and coverage gaps. Underground metro stations, road tunnels, thick walled buildings, remote villages, hilly and forested terrain all create areas where mobile signals simply don't reach. India has made massive progress in coverage, but over 40% of the geographic area still has poor signal. The solution is a combination of government rural tower program, femto cells, tiny tower placed inside buildings, and increasingly satellite internet system like Starlink that beam coverage from orbit. Handover latency. When you are moving and your device transfer from one cell tower to another or switches from Wi-Fi to 4G, there is a brief interruption. This is called handover. For most applications, you never notice it, but for a 5G autonomous vehicle traveling at 120 km per hour, the handover must happen in microseconds or the car's network connection briefly drops during a critical moment. Challenge 3. Security and privacy. Vulnerability. One of the most critical and most frequently examined challenges. Your mobile phone travels everywhere, connects to network you don't control, stores your banking details, health records, personal photos, location history, and private conversations, and fits in a pocket. That combination make it uniquely vulnerable. Let me walk you through the threat landscape. Six types of mobile security threats. Network threat. Eavesdropping on public Wi-Fi is the most common. When you connect to free airport Wi-Fi or cafe internet, That network may not be legitimate. An attacker can set up a fake hotspot with the same name. And when you connect to it, they can see everything you send and receive that isn't encrypted. Man in the middle attacks intercepts your communication and can read or modify app-based threats, malware, and spyware disguised as a legitimate applications. A fake HDFC Bank app that looks identical to the real one but steals your login credentials. A flashlight app that secretly tracks your location and sells it. The Google Play Store removes thousands of malicious apps every month, many after they have already been downloaded by thousands of users. Physical threats. Your phone is stolen. Without strong authentication, Face ID, fingerprint, PIN, the thief has immediate access to your email, your banking app, your photos, everything. Physical theft of a mobile device is one of the most direct and complete data breaches possible. Identity threat. SIM swapping is a sophisticated attack. The attacker calls your mobile operator, pretends to be you, and convinces them to transfer your phone number to a new SIM card that the attackers control. Now all your OTPs, the one-time password for banking, for UPI, for email are delivered to the attacker's device. This attack has been used to drain bank accounts completely. Location threats. Your phone knows where you are at all times. GPS stalking, where someone installs a location tracking app without your knowledge, is used in domestic abuse cases worldwide. Many apps connect your precise location and sell it to data brokers. Advertisers can track your movements across physical spaces. Data leakage. Many apps request far for more permissions than they need. A calculator app asking for access to your contact and microphone. App permission that seems harmless enable systematic collection. Cloud backup breaches expose personal data when backup services are compromised. Now, why is mobile security harder than desktop security? Six reasons. Mobile devices connect to many different networks, each potentially untrusted. A desktop sits on one trusted corporate or home network. Open app stores have millions of apps waiting, all of them is impossible. And malicious apps regularly slip through. Mobile devices are always on, always listening for notification, always connected. There is no equivalent of shutting down for the night. Physical portability means physical loss or theft is a realistic threat, rarely an issue for a desktop. Android fragmentation means millions of devices use run old OS version with no unpatched security vulnerability. User behavior. People ignore certificate warning, use 1234 as their PIN, click suspicious links, install apps from unknown sources. Next challenge is limited processing power and resources. This is one is easy to understand but important to explain precisely in an exam. The core problem: mobile devices must balance three computing constraints: performance, battery life, and physical size. Maximizing any one of these compromises the other. A more powerful processor needs more power and generates more heat. More heat in a sealed device with no fan causes thermal throttling. The processor automatically slows itself down to prevent damage. Look at the comparison table. This is pure exam gold. CPU, a flagship smartphone in 2024, has an 8-core ARM processor running around 3.3 GHz. A high-end desktop has a 16-core 8086 processor running up to 5.8 GHz. That's roughly 50% faster clock speed plus double the core for sustained parallel workloads. RAM. A flagship phone has 8 to 16 GB of LPDDR5 memory. A desktop workstation commonly has 32 to 128 gigabytes of DDR5. This difference directly limits how many apps can run simultaneously and how large the files you can work with can be. Storage. A top-end phone has 512 GB. Desktop system routinely has 1 to 4 GB NVMe SSD. This limits the number of photos, videos, apps the device can store locally. GPU. This is the biggest gap. A mobile GPU has a thermal design power of around 15 watt, meaning it can only generate and dissipate 15 watts of heat. A desktop gaming GPU operates at 350 watt. That's a 23 times difference in a power. The gap in gaming performance, 3D rendering, and video encoding is enormous. Cooling. A smartphone has no fan, no heatsink, no active cooling at all. It relies on the metal chassis to dissipate heat during sustained heavy tasks, gaming for 30 minutes, processing a long video. The phone gets warm and the processor throttles. A desktop has fans, liquid cooling, large heatsink. It can sustain peak performance indefinitely. Screen 6 to 7 inch versus 34 to 32 inch. For professional work, coding, design, data analysis, video editing, screen real estate is a fundamental constraint, not just a comfort issue. The practical implication. Editing a 10-minute 4K video takes 20 minutes on a flagship phone and under 2 minutes on a desktop workstation. Running a machine learning model that trains in 5 minutes on a desktop can take hours on a phone. The solution direction is cloud offloading rather than doing heavy computation on the device. Send it to a powerful cloud server, so the computation there, and send the result back. Google Stadia, Microsoft Azure, gaming, and cloud-based AI assistant all use this approach. Challenge 5. Screen size, usability, and input limitations. This one might seem trivial compared to the security or processing, but it profoundly limits what work can realistically be done on the mobile device. Three areas: UI and display challenges. A 6-inch screen has roughly 1 by 16 the display area of a 24-inch desktop monitor. Try to imagine your entire computer desktop compressed to a 6-inch rectangle. That's what every complex application faces on mobile. A code editor on mobile loses the file tree, the terminal, the debugger, the full syntax highlighting. A spreadsheet loses most of its columns. A Photoshop equivalent loses half its tool panel. Reading small text in bright sunlight is genuinely difficult. The sun washes out the display even at maximum brightness. This is not a small problem for outdoor workers. Text input difficulty. The touchscreen keyboard is genuinely slower and less accurate than a physical keyboard. Studious consistently shows that average user type 40 to 50 words per minute on a touch screen versus 70 to 80 words per minute on a physical keyboard. For students writing assignments, journalists filling stories, programmers writing code, this difference matter enormously. Autocorrect helps with everyday text but actually hinders technical writing code or specialized terminology. The fat finger problem. Fingers are not precision pointing device. A finger tip covers approximately 44 to 57 square pixels when touching a screen. Tapping a small button, selecting a specific word in a long paragraph, right-clicking in a complex UI, all of these simple desktop interactions become frustrating on mobile. Solutions. Foldable phones like the Samsung Galaxy Z Fold unfolds to 7.6 inch, closer to a small tablet while fitting in a pocket. Voice typing reaches 98% accuracy. Gesture navigation reduces button dependency. Samsung DeX connects a Samsung phone to a monitor, keyboard, and mouse. Give you a full desktop-like UI. The phone becomes the computer. Next challenge. Interoperability and standardization. This is the challenge you feel as a user but may not have a name for. The core problem. The mobile world is fragmented, hundreds of device manufacturers, multiple OS versions, dozens of network standards, and thousands of apps all needing to work together seamlessly. They often don't. 4 layers of fragmentation. OS fragmentation. Android is the dominant mobile OS with over 70% global market share. But Android is not one thing, it is a family of versions. Android 14, 13, 12, 11, 10, and even older versions are all actively being used simultaneously across hundreds of millions of devices. Google releases major Android updates annually, but device manufacturers are slow to push updates to their devices, and many people never update. An app developed for Android 14 must be tested against all older versions to ensure it doesn't crash. An enormous ongoing development cost. Device fragmentation beyond OS version. Android runs on thousands of different physical devices, different screen size from 4 inches to 7 inches, different processor from Snapdragon to MediaTek to Exynos, different camera configurations, different amounts of RAM, network fragmentation. A mobile app must work on 2G in rural Bihar, 4G in a Mumbai high-rise and 5G in Bangaluru's tech core area. Simultaneously and transparently, the difference in available bandwidth between 2G 50 gigabit kilobytes per second all the way to 10 gigabits per second simultaneously. Designing an app that works gracefully across this entire range is significant engineering challenge. App ecosystem is split. Apple's iOS and Google's Android are essentially two separate planets. Most major apps exist on both, but many don't. Files created on iOS apps often can't be opened on Android equivalent. Accessories built for iPhone won't work with Android until the EU's mandate forced Apple to adopt USB-C in 2024. iPhone and Android users couldn't even share chargers. The developer cost implications are real. Building a high quality apps for both iOS and Android costs roughly twice as much as building for one platform. Tools like Flutter and React Native allow writing on one code base that runs on both, but they come with their own trade-offs in performance and native feel. User experience gap, charging standards, compatibility, these are the real impact and solutions for the fragmentation problems. Next challenge is health, social, and environmental concern. This is a challenge that goes beyond the technology itself. It's about the impact of mobile computing on human beings and on the planet. These are unusual challenges for a technology course, and that's exactly why examiners love asking about them. They test whether students think broadly about technology's real world impact, screen time and addiction. The average smartphone user checks their phone 96 times per day. That's once every 10 minutes or every waking hour. Instagram's infinite scroll, TikTok algorithm, notification system, these are deliberately designed by engineers and psychologists to be addictive. Every like, every notification, every new content piece triggers a tiny dopamine release in your brain. Repeated enough times, this creates genuine psychological dependency. The World Health Organization officially classified gaming disorder as a mental health condition in 2019. Physical health issue. Text neck is a real medical condition. Chronic neck and upper spine strain caused by repeatedly bending your head forward to look at a phone. Study shows that a 60-degree forward head angle typical when looking down at phone, your neck bears the equivalent of 20 kg of force. Long term, this causes muscle damage, spinal issues, eye strain from prolonged close range screen use, sleep disruption from blue light suppressing melatonin production at night. This is a public health concern that affects hundreds of millions of people. Electronic waste. This is genuinely alarming. Over 50 million metric tons of electronic waste are generated globally every year. Mobile phones have an average replacement cycle of 2 to 3 years. People buy new phones because they slow, because they are out of style, because the battery is degraded. Each discarded phone contains toxic materials like mercury, cadmium, and arsenic in batteries and circuit boards. When these are dumped in landfills in developing countries, they contaminate soil and groundwater. The right to repair movement in modular phones like the Fairphone designed to be repaired rather than replaced are emerging solution. Digital divide. Perhaps the most serious challenge on this slide. 40% of the global population, roughly 3 billion people, still lack reliable internet access in India, while urban areas have excellent 4G and growing 5G coverage, vast rural areas remain underserved. This means that all the benefits we covered in the previous lecture, mobile banking, telemedicine, learning, mobile commerce, are unavailable to the people who arguably need them most. India's BharatNet program and satellite internet are working to close this gap, but progress is slow. Next challenge is quality of service, QoS, and reliability. This is the most technical challenge in this lecture and it's a very common exam topic, especially for 5 and 10 mark question. Definition: quality of service or QoS refers to the ability of a network to guarantee a certain level of performance for a specific application or users. In mobile computing, maintaining QoS is extremely difficult because the environment is constantly changing. 5 key QoS parameters: throughput, the actual data transfer. Data rate is achieved. Note the theoretical maximum, but what the user actually experiences. A video call requires a minimum of 1.5 Mbps throughput to avoid freezing. Netflix HD requires 5 Mbps. If the available throughput drops below this threshold, the service quality degrades. Visibility, latency, the round trip delay between sending data and receiving a response. 4G networks typically have 50 to 80 milliseconds of latency. For web browsing, this is imperceptible. For computing online gaming, 50 milliseconds is too high. Gamers need under 20 milliseconds. For remote surgery using a robotic arm, over a mobile network, even 10 milliseconds is too much. Packet loss. In any network, some data packets don't arrive at their destination. They get lost due to interference, congestion, or routing error. For downloading a file, packet loss causes a retry and a slight slowdown, usually unnoticeable. For a voice call, more than 2% packet loss causes the audio to sound choppy with the syllables missing. For a real-time application, packet loss is catastrophic. Jitter, the variation in timing between packet arrivals. Even if average latency is acceptable, if packets arrive unevenly, some fast, some slow, real-time applications suffers. Video calls look smooth when packets arrive at regular intervals. If intervals vary widely, some packets arriving in 5 milliseconds, others in 200 milliseconds, the video becomes jerky. Jitter buffers help smooth this out but add their own latency. Availability. Percentage of time the service is accessible to users. 99.99% availability means only 52 minutes of downtime per year. This is the standard target for mission. Monitoring these cannot tolerate outages. Now the QoS improvement techniques, traffic prioritization. Different types of traffic gets different priority levels. An ambulance mobile command system gets highest priority. A live video call gets high priority. A background app update gets lowest priority. This ensures critical communication aren't disturbed of bandwidth during congestion. Adaptive bitrate streaming. YouTube and Netflix dynamically adjust video quality based on current bandwidth, prevents buffering. Drop from 4G to 3G coverage. Within seconds, the resolution drops from 1080 pixel to 480 pixel. The video continues playing without buffering. The quality degrades gracefully rather than stopping. Edge computing. Instead of sending your data to a distant cloud server and waiting for the response, process it at a nearby edge server, perhaps just a few kilometers away. This can reduce round trip latency and from 100 milliseconds to under 10 milliseconds. Autonomous vehicle and remote surgery depend on edge computing. Content delivery network. Popular content pre-stored on local CDN servers. Indian users get Netflix content from Mumbai, not the US. When you press play on a Stranger Things, the video comes from a server a few hundred kilometers away, not from the US. Network slicing of 5G innovation. The physical 5G infrastructure is divided into multiple virtual networks, each with guaranteed QoS. A slice from emergency services with guaranteed low latency. A slice from IoT sensors needing massive device density. A slice from consumer wanting high speed, all sharing the same physical infrastructure but with isolated guaranteed performance. This is the master summary table. 8 challenges, their core problem, key, key real world example, and solution direction all in one place. Pause right now and photograph this or write it in your notes. Battery life, finite power depletes with use, 5G radio use, 28% of battery, fast charging, ARM chips, power management, bandwidth shared spectrum congestion, IPL stadium, slow internet for all, 5G massive MIMO beam, forming security, wide attack surface, many networks, public Wi-Fi, eavesdropping attack, encryption, VPN biometric on. Processing, CPU, RAM, storage constraint, video editing, mobile versus desktop, ARM efficiency, cloud offloading. Usability, small screen touch input limits, writing code on a 6-inch screen, foldables, voice input, Samsung DeX. Interoperability, OS device network fragmentation, Android has 10 plus active version, Flutter, React Native, Meta standards. Health environment, addiction, e-waste, digital divide, 50 million tons e-waste per year, right to repair, BharatNet recycling. QoS and reliability, unpredictable changing condition, video call drops in underground tunnel, edge computing, adaptive bitrate, 5G slicing. Today we covered the 8 challenges of mobile computing not as a list to memorize, but as a deeply interconnected set to trade-offs that reflect the fundamental physics and engineering realities of building computing into devices that go everywhere. Battery life is limited because portability requires battery power. Bandwidth is limited because wireless spectrum is shared. Security is harder because connectivity creates attack services surfaces. Processing is constrained because power and heat are physical limits. Usability suffers because small is a physical constraint. Interoperability is hard because the mobile ecosystem is genuinely fragmented. Health and environment impacts are real and growing. And QoS is hard because the mobile environment changes constantly. Every challenge has engineer working on solution. 5G solves many of the networks challenges. Foldable screens and voice inputs are addressing usability. ARM chips and fast charging are transforming the battery situation. Edge computing is revolutionary QoS, but the challenges don't disappear. They evolve. Thank you for watching this video. In the next lecture, we compare mobile computing with distributed computing, a topic that always comes up in exam and is fascinating once you understand the difference. Subscribe and hit the bell so you don't miss it. If this lecture helped you, please like the video and share it with your classmates. Drop a comment below. Which challenge do you personally find most frustrating in your daily life? I read every comment and reply. See you in the next lecture. Thanks for watching.